Welcome to the 6th unit of the module. Here we will be discussing mainly the design of hardware control unit. If you look at the last few units, we are basically discussing that basically for a macro instruction, what are the micro instructions, and for each micro instruction, what are the basic control signals required and how they can be generated, or for each given micro instructions, what are the control signals to be generated and what is the proper sequence for that. Then now onwards, we will be basically looking at how we can generate that. What are the basic circuits or what are the basic techniques of basically generating those control signals. As we have already discussed in the summary of the module, that basically there are two types of manner in which you can generate the control signals. One is actually called the hardwired, which we are going to do today, and another is basically called microprogram based. So, one is a hardware based and one is a software based. So, in this unit basically we will be focusing on the hardware based control unit, in which there will be a dedicated hardware which is hard coded and which will generate the control sequences, control signal sequences based on the control instructions. So, basically if we first look at the unit summary, we know that basically there is a set of micro instructions for given any set of macro instructions. Then basically what happens, we have seen that for a given instruction, there is fetch, decode and execute. There are sequence of micro instructions corresponding to each phase, and for each of the micro instructions there is a sequence of control signals to be generated, like program counter out, memory address register in, set the read mode to the memory, then wait for the memory to give a signal that it is ready, etc. So, basically depending on each of the cycles, that is we have seen that some steps, like in step 1, 2, 3 basically corresponds to fetch of the instruction. After that it basically corresponds to the execution of an instruction. So, based on each of the phase or each of the steps, we have to generate these signals, control signals. So, how we can generate them? There can be basically two approaches. One is called hardware and another is called the microprogram. In hardware, basically what is going to happen? We will have a dedicated finite state machine which will move from one state to another, and each state will correspond to one time step of the micro instruction, or one time step or one micro instructions basically, and the control signals therein. Then whenever you move from one state to the another state, it is basically nothing but one step of the micro instruction to the another micro instruction. Basically we have seen that first three are basically corresponding to the say phase, fetch of an instruction. So, first three states of the finite state machine will be corresponding to the fetch phase, and basically whatever signals like PC out, MDR in, make read, etc. will be the output of the corresponding finite state machine based states. Because we know that in this unit basically if you have forgotten, you have to basically revise the concepts of designing of Millie and Moore machine given a truth table implementation. Then you have to understand and recollect from your digital design fundamentals that how a finite state machine can be implemented, and based on some inputs how the outputs can be generated. So, in our case the inputs will be nothing but the different states, output of the instruction register, then flag registers, and some signals which will be coming from the data bus, which will be coming from the bus, that is your signals from the external memory, etc. And then it will generate some outputs which will be corresponding to each state, and as I told you, each state corresponds to a step or a micro instruction, and the output will be the signals. And this is actually hardware. Why we call it hardware? Because corresponding to each macro instructions, we know what are the micro instructions, we will generate a finite state machine and it will be hard coded. But the same thing can also be done using a software approach which is called a microprogram based, which we will look at later. But in this case basically everything is hardware in terms of the finite state machine states. So, therefore, actually we call it as a hardware design. And in fact, a hardware control we have to design the finite state machine in terms of gates and flip flops. So, basically as I told you, we have to again recollect that given a sequence of inputs and outputs and states, we have to recollect how a finite state machine is designed. Basically as I told you, the inputs are from the instruction register, control flags and status registers and control flags, some external signals, and the control step counter. That is very important. What is a control step counter? It is nothing but if you have a finite state machine which goes from one step to another. So, also you have to know that what are the values of the state variables at that state. That will also depend on, say for example, in this state the variables are say 1, 0. So, the output will also depend on the value of the present state, which is a very standard terminology when you are saying FSM implementation in terms of circuits. The outputs are of course the different control signals which go to the CPU or the memory. So, based on your instruction register, external signals, condition code, that is your flag, and control step counter. Control step counter is nothing but your state in which you are in, the decoder or the encoder, that is the which is going to generate the signal. For that, based on all the inputs, there is a decoder, or there will be decoder and encoder combination, that is a sequential a combinational circuit will be there, which will generate the relevant signals, control signals at each of the finite state machine base state. So, in nutshell, what we are going to see today, we are going to see different type of instructions and the micro instruction therein we will see, and then we will see how a finite state machine is designed, which is hard coded, because anyway a finite state machine is hard coded, because that is not flexible, and how it generates the corresponding control signals. That is what is the summary of this unit. So, what are the unit objectives? At this unit, you will be able to, there is an analysis objective, you will be able to associate the control signals by looking at the control steps of each instruction, that is a micro instruction, and the processor, and to implement the control signal by digital logic circuit. That means basically you just, if you look at the sequence of micro instructions and the control signals therein, you will be able to basically associate for which state what of the signals will be there and how the finite state machine can be designed. So, again for this basic design of finite state machine we will not be covering in this unit, because it corresponds to your digital design fundamentals. So, if some truth table is given, so how you design a finite state machine in terms of gates and flip flops, that you have to recollect back. And finally, there is a design objective, design issues and implementation of the control unit. So, if I give you a macro instruction, you will be able to design a finite state machine based controller for that. That is what is the idea. So, now let us go into the unit. So, basically this is what is your block diagram of a hardware control unit. So, what is there? As I already told you, the heart of the input is instruction register, because you will have an opcode and then the operands. So, the opcode will basically tell you what is the correct instruction and what are the control signals required for that. For example, if it is a load instruction, you will have different. If it is a store instruction, it will be different. That means the micro instructions corresponding to that. So, if it is the fetch part, then some different step has to be done. If it is the add, you are really going to add the two operands, then different different stuff has to be done. So, all these things will be basically controlled by the opcode, which will be in the instruction register. So, that is the heart of the control of the control unit. Then of course, you have external inputs. So, what are the external inputs? Like your memory block is saying that I am already done with the reading or writing part, then you can access my memory data register. So, that is what, there are some condition codes. So, these condition codes basically are, you can understand that these are something like your flags, basically the flag registers. So, the flag registers will directly tell you that whether the 0 flag is set, the sign flag is set, etc. So, those inputs also has to be taken if it is a conditional instruction, because conditional instructions will always depend on inputs of the flag registers. You can consider this as a flag register. And finally, there is something called a control step counter, that is step 1, step 2, step 3, from some step there may be an if then else condition, like if 0 is set you do something else. So, the finite state machine implementation, also the state bits will also give as these are input. Taking all these inputs, basically you are going to generate some control signals which are going to generate the control signals. These signals are like PC out 1, PC in 1, a memory register out 1, etc. So, basically or add 1, subtract 1, multiplexer bit select 0 or 1. So, all these things will be generated by looking at all the inputs. So, these were already we have discussed like IR, external inputs and conditional codes. Here only important thing is that as you have to go in steps, like for add R1, R2, say 5 steps are there, add R1, M, maybe 6 stages will be there. So, there will be a finite state machine which will be involving these 6 stages, and all these, and also depending on what state you are, the control signals will change. So, that state variable as an input will be given by the control step counter, and obviously a clock will be driving it, because it is a finite state machine. So, now basically if such an input is given like IR inputs, external conditions, control step stuff, then how you can design this decoder or how you can design an FSM out of it is a standard digital design procedure which you have to read which you might have already read in your digital design fundamentals, and you have to recollect them back. That is a finite state machine synthesis. You can use any kind of flip flop like JK, SR, D, whatever you require, accordingly you can design this circuit. So, basically whatever I told you, you can read over this slide. It says that hardware control unit is a sequential state machine, that is a finite state machine which will generate the sequence of controls. As it is a finite state sequential machine which is hard coded, so we actually called it as a hardware control unit, because once the finite state machine is synthesized, you cannot change that. And the output of the finite state machine basically will generate different control signals which will be given to the ALU, the read or write part of the CPU, write part of the memory block, etc. And of course, you can tell add or subtract or multiply, etc. to be done. For example, they have given a simple example. Say when you want to read an instruction to IR from the memory. So, generally write MDR out, IDR in. That means basically we are saying that memory has already given the value to the memory buffer register or the data register, then I can actually put it into the instruction register. Say maybe it is happening at state number 3. So, basically what is happening at state number 3, basically the output will be MDR out equal to 1 and IR in, that signal will be equal to 1. All other control signals will be equal to 0. So, basically in this case we just need to depend, there is no input responsible here, we just need to see the control bits or the state variables for state number 3 should match, and then you can easily generate out the signal. So, in this for this simple thing that MDR or IDR in, there is no required to think about any inputs in this case, unlike for some other cases like where you have to wait for the input signal that the memory is ready. So, maybe at some other stage from coming from here to here, you WF MC equal to 1. So, you have just waited that the MFC is 1, that means the memory has already told that whatever data you are asking from the memory has already been dumped to the memory buffer register, and now you can read it. So, by getting this input signal you come over here, this is an input and then maybe we do not have any output correspondingly, but at this stage what happens, you just need to know that I am in state 3, that is you just depend on the state variables and just generate the output MDR out equal to 1 and instruction register equal to in. So, basically in this case only your hardware control unit will depend on the state variables as the input. So, just as a very stray example to show basically how it works. And then basically what happens, we will finally have a decoder, encoder and series of flip flops which will design the basic circuit, which will take all these inputs and generate the corresponding output signals and in the proper sequence of steps of a finite state machine. So, it is a finite state machine based synthesis you have to learn. As I again repeating, the inputs are IR, condition bits, flags, status registers and basically your control step counter. Control step counter is nothing but your steps of the finite state machine. The outputs will be basically your some control signals which will be giving it to the different parts of the code like your ALU, memory read, etc. Again now, so this is actually very straightforward, whatever I have discussed I have written in this slide, you can go through it. Then what are the advantages of a hardware control unit? It is a speed. So, whenever you have something implemented in hardware, it is extremely fast. Disadvantage is that basically it is hard coded, that is you cannot change. So, given a micro instruction set or a macro instruction and the corresponding micro instruction, this is what is very hard coded. When we will be going for the microprogram based control, you will find out that is slightly slower, but there is not a flexibility there. So, that you can appreciate only when we will be discussing in the microprogram based control unit. For the time being, just understand that it is the hardware based implementation, no flexibility a disadvantage, but fast implementation is the advantage. So, again slightly more detailed diagram, basically what happens. So, there is something called the instruction register. So, the instruction register actually will feed to a instruction decoder. Basically, this part is nothing but your off code. So, it is going to tell you that say if it is a load instruction or if it is an add instruction, which finite state machine basically you have to choose, because for load there will be a separate finite state machine, for add there will be a separate finite state machine, because a load means there is series of micro instructions for that. Fetch the instruction in trace stages, then you decode, and load means you have to again look at the memory and dump the value. So, you have already seen that for a load R1 R2 and for a load R1M, the sequence of micro instructions will be different. So, based on the off code or if it is an add instruction etc. So, based on the off code it will give the inputs to a decoder. The decoder will actually make the corresponding 1 bit as high. So, if there are M instructions, so it will be a decoder of M and input will be log 2 M cap. So, that means the idea is, say for example, if there are 64 instructions possible, then 2 to the power 5. So, there will be actually 5 bit will be your off code. So, off code can generate 6 to the power 5 is 32, 2 to the power 6 is 64. So, basically sorry, it is a 6 bit input. So, you can generate all the numbers from 0 to 2 to the power 6. So, it will generate all the numbers, this is 6 bit. So, you can generate all numbers from 0 0 0 0 0 0 to all ones. Correspondingly basically it can generate the this is a decoder. So, any 1 bit out of the 64 inputs will be a 1, which will correspond to the micro instruction or basically the finite state machine corresponding to that macro instruction. Say for example, for load maybe the off code is all zeros. So, in fact, it will first make this bit as 1 and the INS1 will actually invoke the finite state machine corresponding to the load. Maybe 1 1 1 1 1 1 1 1 is the opcode for the instruction. Add. Then whenever all the IR will give the value of 1 1 1 1 1 1. When it will go to the instruction decoder, it will make INS M equal to 1. Then INS M equal to 1, this bit will correspond to the encoder, it will actually activate the finite state machine which corresponds to the micro instruction implementation for add instruction. That way it goes. External inputs are always similar, as I told you, they have nothing to change, that is your instructions or signals from your process memory etc. Condition codes are the flag registers which will be given to the encoder, and this is a step decoder. Step decoder is nothing but T1, T2 up to Tn. So, T1, T2, Tn are basically the steps. So, for example, if you are at state 0, T1 will be high. If you are at step 1, T2 will be high, and so forth. Or you can even think of a binary encoding. Like for example, if the state 0 is there, all Tn's will be 0. If it is state 1, so it will be 0 0 0 0 1. So, that way it can be a binary encoding or it can be a hot one encoding kind of a thing, like in state 1 it is a 1, in state 2 it is a 1, and so forth. So, anyway, this encoding is the way to minimize the circuit, but for explanation just you can understand that for given any state a proper encoding will go in. Step controller counter is basically generates the movement in the finite state machine. Taking all these inputs, it will generate the control signals. So, in fact, what happens then in a nutshell, your instruction register will give the opcode corresponding to an instruction. Based on that, any one of the signal will be made high that corresponds to that macro instruction. Based on this, you will invoke the finite state machine which will correspond to that macro instruction, and then you will move through the sequences of steps based on the external inputs and the condition codes and as well as the steps, because step 1 some signals will be generated, step 2 some instruction will be generated, and it will keep on actually moving 1 2 3 4 5 6. If then else condition, then you can have to move from one step to another, but otherwise there is a incremental value of the steps. So, I have written that basically in the text, you can read over it. So, what it says that the opcode will actually generate signals I1 to IM. So, if there are M signals based on an opcode, any one of them will be high, and that will actually invoke the corresponding finite state machine. Corresponding, then the decoder examines the signal and accordingly the relevant control signals are made high by the encoder. In fact, actually it will select a corresponding finite state machine. Say for example, they are saying that the correct instruction is K. So, that is INS K will be invoked. For example, that is what he is saying, that INS K is invoked. So, if the K instruction, then this is going to be invoked, and then let us saying that assume that you are in T equal to 1, that means maybe this is we are in the first stage. So, whenever INS K equal to 1, so that means the kth instruction corresponds to the opcode of the current instruction which is in the instruction decoder. So, INS 1 will be the 1 by the decoder. So, when it is the case, the corresponding finite state machine, like you will have lot of states and this. So, this one is going to be invoked and maybe you are in state S0. Then whenever I will move to state, this is T0 assume, this is T1, then at time T1, after first step I will go to T1, and maybe in that state basically you are going to take appropriate actions, like you can make the MDR out to IDR in, that is you are going to read this, some step can happen. So, basically this is how it happens. So, corresponding to the INS, that is instruction type based on the opcode, a corresponding state machine will be invoked, that is you are going to the initial state. After that, depending on this one, that is your step controller, you will go to step 1, step 2, step 3 and that forth. Maybe in this stage you do not have any input, you just generate MDR out and IDR in. So, thus corresponding signals will be generated and you will go forth. So, that is how it basically happens. You can read this slide and also I have explained you. So, basically you can get a very quick understanding what is happening. Whenever we are going to now take some concrete examples which will make this step absolutely clear. Only thing you remember, then based on the opcode, only one bit for the corresponding instruction will be made high, that finite state machine will be invoked, and after that you will go step 1, step 2, step 3 based on the counter, that is your stage counter we call it, that is your step counter, and then at each step you are going to read some flag values, some input values, some other values, and you are going to generate the corresponding control signals. That is how it happens. Now, we will take some very concrete examples and the thing will become very, very clear for us. So, first let us take an example called add R1M, that is you are taking the memory location value R1, dumping it to R1 after adding it to what was the content in R1. If you forget about last class, we have discussed that these are the series of control instructions. What are the signals involved? Program counter in, program counter out, Z in, FMC, all the signals whichever we are listed here are actually utilized for this micro instruction, sorry, the micro instructions which will be involved in this macro instructions. So, they are all will be generated. So, now first if we remember that first was program counter out, that is the PC value will be fed to the memory address register, and then you will make it select 0 Z add in, this part corresponds to incrementing of the value of PC. So, whenever I say PC equal to Z in out, that means the PC is increment, sorry, this way. So, whenever Z out means the value of incremented value of PC will be dumped into PC output, because Z output actually was storing the value of the accumulator, sorry, the value of the ALU, which was added the value of program counter plus the constant. Now, we have to put it in PC, that now PC is updated. Now, we have to, here is important, we are waiting for an external signal, this is an external signal. So, this is an external signal. So, we have to wait for the external signal only once when it is ready. In stage 3 basically what you can do, the instruction which is now in MDR can be loaded to register in, and familiarly you can go ahead. So, then again there is a external signal and all others are internal signals like PC out, MIR in, read, they are all signals which are generated, and here we are waiting for something which is again a condition which I am depending on, which comes from an external one. So, all these like PC out, MIR in, read, select 0, add Z in, they are the control signals which you have to generate, and then WFMC is something on which you have to wait till you can go to the third stage. Similarly, from the fifth stage to go to the sixth stage, basically you have to again wait for the WFMC. That means this round circle, these two are basically inputs which on which the movement of the finite state machine will depend, and all other signals are basically being generated, which has to be generated by your hardware control unit, which in this case is a finite state machine. Now, we will first basically see the circuit and then we will go for the discussion. So, let us assume that this add R1 M, whatever may be the opcode for this, corresponds to first instruction. So, what is going to happen? INS1 will be 1, that in the decoder the first line will be 1, which corresponds to this instruction, which is the first instructions. So, whenever the INS is 1, because it is a decoder, so only one line will be 1. So, only this finite state machine will be invoked, because if you look at the initial stage, its input is INS1. So, only if the value of INS1 equal to 1, then this machine is invoked. And you know there is already a decoder. So, based on the input of the opcode, only one of these machines will be invoked. Like there will be another machine for INS2, another machine for INS3 dot 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 up to INSM. So, based on which instruction is in the instruction decoder, the opcode, it will be correspondingly invoking only one finite state machine, because correspondingly this input is equal to 1. Now, next what? Let me zoom this part, so it will be a bit clear. So, next stage what I am doing, so you are invoking this finite state machine based on the output of the instruction decoder INS1 equal to 1. Next what? Next I am going to go to state 1. So, what is the output? Initially state is there. From state 0 to state 1, what happens basically? You should know that now I should be in state T1, that is from 0 next state has come, that is counter has now become 1. Then what are the outs? If you remember, there is only one thing over here. After initial state, basically you need not depend on any other input. Only thing is that state 1 corresponds to the fact that at present the instruction is INS1, that is add R1 M register to memory. Then next is nothing, just you need to wait till T1 comes. T1 comes means that the sequence counter has now become 1. So, what is that? Now, after that there is no other input required, only time has passed, the clock has come, that from stage 0 to stage 1 you can go. And what are the signals out? PC out, MAR in, read 1, select 0, add 1, Z in 1. So, all these signals will be correspondingly generated at this state, and all other signals which are not shown like MAR in is 1. So, what about MAR out? It will be equal to 0, like PC out equal to 1. So, what about PC in? It will be 0. So, whatever are not shown here are made 0. Now, it is important. So, now in this case you have said that I want to read the memory. In the memory address register you have given the value of PC, that means you are going to fetch the instruction. Second stage is instruction. Second stage is interesting basically. So, when I am in state 1, again you are waiting till you go to the second stage, that is second clock pulse, that the counter has become 2. Not only here, you have to again wait here for another external symbol, that is WFMC, that MFC, that MFC you have to wait. This is another signal which will be coming from the memory to the bus. It is going to tell that now the memory has been read, everything is fine, now you can go ahead. Only after this you can go to the next state. So, what is the next state? You are saying that PC in equal to 1 and Z out equal to 1. That is, you are going to dump the value of program counter with an updated value from Z, which is nothing but which contains the value of ALU. But before initially there is only one input which you are depending on, that is your clock counter, that is state 1. Here you are depending on 2, that is clock counter, as well as you are waiting till the memory is ready. So whenever the memory is ready, you can go to the next step, S2. There is nothing else you have to depend on, just the timer, because already the memory signal has been ready in the previous state, just you dump the value of memory data register to the instruction register. After that, just the sequence, because there is no if then else condition, you did not wait for any memory read here. So the memory data register out, that is basically your instruction, has been now loaded to the instruction register. For state 3, nothing you have to do, just you have to wait for the next clock pulse, which will make the state equal to 4. Here instruction register out will go to the memory address register in, because you have to fetch another operand from the memory. If you remember, your instruction is R1M. The next instruction is available in the memory location. So what you are going to do, instruction register out, that is M in the instruction register, is dumped into the memory address register, and you are making the register mode as 1. So these are the control signals which will be generated. All other not mentioned, like memory out, R in, they are all zeros. Then again I go sequentially to the next state. Here also I do not need to depend on anything else, except it is important over here, I have given a read signal to the memory. So I cannot only depend on the input. So only input here is T5, that is state 5 is going to come, the counter is 5. I cannot depend only on that. Here again I have to wait till the memory gives a green signal that I have done, you can read it. So whenever it says MFC, that means I am done. So then you can go for, here actually MDR in is 1, that means you are going to generate the signal that I want to read the memory. Because till here it is memory address, you have given the value of the register value M, and you are saying read equal to 1. So you have said that the memory is a read mode. So this one says that memory is been read, a green signal has been there, then only you can give the corresponding signals. Like here already MFC has been 1, right. MDR in means you are going to get the value of the memory into memory address register, but now you cannot read here, because you cannot read at this stage, you cannot read basically the value of MDR, because I am waiting for the memory location to be done. Here I am giving a read signal, but when I am going to state 6, that means already this has been over long back. So I can go for MDR out equal to 1 and all other similar procedures, like this signal has been done. So if you remember, for all other states similarly I can complete all the sequences of the state machine design. Like for 6, this is the state 6, that counter is 6, I will generate the corresponding control instruction. 7, I will generate the control signals correspondingly. 8, I will generate the corresponding signals correspondingly. Finally end equal to 1 means you have to stop this set of micro instructions and the macro instruction is over. So what is to be emphasized is very easy to understand, only some clocks are there. First is this machine is invoked, that is the initial state condition enabling is INS1, that is based on the opcode. Only when the signal is 1 you can go to that corresponding state machine. If there are M instruction, M such state machines will be there, and based only on the output of the instruction register via the decoder you can invoke that corresponding state machine. Now for all cases, generally if you do not want to wait for any kind of an external input like your condition flags or your memory values, output of the memory, that is memory is ready, or there is some signals like you want to wait that if the flag is 0 or flag is 1. So if no such conditions are there, you just need to wait for the time, stage 1, stage 2, stage 3, these are generated by the clock and the FSM counter. Go to stage 1 and generate all the corresponding signals which are required to do that. Only here, like whenever you have given a read signal to the memory, so you have to wait till the memory says that I am ready. So in that case the input from this state to this state, the transition will depend on two inputs, one is the state and one is the external signal, and then you generate the corresponding signals. Like on this case it will be similar, but here again I have to wait for the memory to be ready, because here I have given a memory read, this is a memory read state, that T4, and you are going for IR out, that is the instruction register you want to read from the operand from the memory location M. So in the memory register address register you are giving the value M and you want to read it. So at least you have to wait for some amount of time till you can get the value of memory data out to your some kind of the another operand Y where it will be stored. So this reading can happen only when if the MFC is ready. So only in that way it can be done. Okay, so in this way you can explain the whole thing. So that 6, 7, 8 are just sequential part, and then finally you are going to generate the end out of it. So this is the finite state machine corresponding to the set of micro instructions corresponding to the macro instruction R1M. That is, you first write down these control steps, control signals steps, then you find out what are the inputs. There are two inputs only here, WMFC, WMFC, and all others are signals to be generated, and of course 1, 2, 3, 4, 5, 6, 7, 8 are the sequence numbers. So you have inputs like sequence number as well as WFMC. So these are the two inputs, and for all other cases you have to generate. So similarly you can map this to the finite state machine I have shown you, and then you have to just go for finite state machine based synthesis and your job is done. How to generate a finite state machine from a finite state machine design, how you can generate in terms of gates and flip flops is just a simple digital design fundamental which you can read and go back and read your second semester textbooks. This is what is written in the language. You can read through the slide basically, and you will get a very clear idea. Like say in control step 1, the values are this one. So you have to generate these values directly, and all other signal values are 0, which I have already told you. At T2, you have to wait for the external signal FMCB to be 1. So basically there are two inputs for the second stage, that is your clock counter, the stage counter, as well as the signal from the memory, and then you generate the PC equal to 1. Similarly, in this way you can generate the whole circuit, whole finite state machine, and then you can synthesize this. Like this is about basically your state generation. In state 1, basically you have to check whether the T1, that is state 1 is equal to 1. So that is, this slide is basically saying that from one state to another state, the transition depends always on something called the state counter, that is T1, T2, T3, that is the states, that it will depends on state counter, that I can go from state 1 to state 2 only if the state variables have been implemented. This is just a finite state machine based implementation. So whenever you want to implement a finite state machine, you remember that always you have to increment the states like 0, 0, 0, 0, 0, 1, 1, 0, 1, you have to generate the forward counter. So that only can translate into a sequential machine in states will go through. This is just a simple digital design fundamental. So basically this slide is showing that for all the cases, one primary input for this hardware control is the state counter, T1, T2, T3, they are nothing but the state variable values 0, 1, 2, 3, 4, 5, 6. Along with that, sometimes we will have extra inputs, which in this case the output of the memory. Sometimes it can be flag register values also. Okay. So now basically we are going to, as I have told you, we will also see basically how a flag register can be an input. Till now the last instruction was a simple non-control based implementation, just a flow. But here we are going to see two type of instruction, in which case is an unconditional branch and one will see as a conditional jump. So conditional jump, actually the corresponding instruction will have another input which will come from the flag register, so that you can get a basic idea. So jump to M, as you have already seen, these are the control signals involved. There is nothing much to discuss, you just look at the other previous unit, then you can get through what are the signals to be generated. So these are all the signals to be given as output. This is one input we have to wait for from the memory, and that is it, and all others are signals which has to be generated, right, all others are output signals. So what will be the stuff? So again importantly, assume that jump N is signal number, instruction number 2. So jump unconditional to M is signal number 2. So only when the opcode corresponding to jump M comes, then only this INS2 will be equal to 1. So only the initial state input value will be satisfied only for this finite state machine. For all instructions there are different finite state machines, but whenever you are going to give jump M in the instruction register, the corresponding opcode will actually satisfy only the input condition for this finite state machine. So this will be invoked, and it will not satisfy the initial condition state for the previous instruction or any other instruction in that matter. So only this instruction will be activated. So again, as I told you, stage 1, so counter is 1, you generate all these signals and go to state 1. State 2 basically similar, 2 is the input and you have to wait for the memory to be ready, because you are going to read the memory value, that is instruction in the first stage. So whenever it is ready, then only you can actually start the memory read. So it is generating the signals, and the third stage, because in this stage you have already verified that the memory is ready, so you are saying that MDR equal to I in. So this stage says that memory is ready, so you can actually dump the value of the memory instruction. T4 what? Basically, as you see, the jump unconditional, so you have to take the offset value and actually you have to put it in Z in. Already we have seen, so in this case you have to take the value of offset and select one, add one, Z in. That means what you are going to do, you are going to get the updated value of PC, you are going to add with the offset value of IR, and then you will actually we are going to get the new value of the program counter, that is the jump address, and you will dump that value to PC and your job is done. So, basically, but here there is no condition. So, whatever may be state, there is no input required from any flag register, just you have to take the value of offset value of IR, you have to add it with the program counter value, which is already saved in, if you look at it. So, the PC out and Z in, and of course, which is saved in some temporary register. In that manner, you have to just get the value added, and it will be the new value of the PC. So, in fact, there is nothing to depend upon. So, we just say that IR out, that is instruction. Of course, the offset is taken as output, select 1, add 1 Z in. If you remember, it means that I am selecting the Y variable, not the constant variable, to be added to the present updated value of PC, which will be in the data bus, which will be present in the bus, and the output will be saved in Z in, that is actually equal to PC plus offset value of PC, which is nothing but equal to jump, the value variable M will come to the PC, the value of M will come to the PC. That is state 4. So, once it is the condition, you will come over here, then actually Z out PC in, that is Z out here is nothing but the M, which will be dumped to the program counter, and its N. That means, in this case you are just updating the value of PC to M. It was jump M. So, already we have seen that there will be just a sequence of steps, because it is unconditional instruction. So, only everywhere will depend on just the state, that is whenever the counter will be 4, you can go over here and so forth, and it will be basically end the machine. It is a very simple explanation which you have done. But to appreciate the fact that when there is another input on which your state machine transition will depend, will be clear when you are taking a conditional jump, which you are now going to do. Again, you can just go through this slide, which I have just told you that what will happen after which stage. Like for example, in the jump state, this is the initial condition which is enabled. At T1, state 1, then you are going to generate all these signals. At T2, after the second state counter is 1, you are going to generate the whole signals, and then the whole design can be very easily completed. Most interestingly, now whenever I tell you that the input to the finite state machine will depend on state as well as some external inputs like your memory or your register flags, then you have to take a conditional jump. So, this is a conditional jump on Z to M. So, therefore, if you see, all other steps will be similar. Here we are saying that the offset of IR selected everything, but if flag value is not equal to 0, then end. If flag equal to 0, then you update the value of 0 of PC with M, but if the flag variable is not set, then you go over here and you do not have to do basically anything. Or if the flag value is 0, then you have to update this, that Z out PC in means the update value of PC with, that is M, will be dumped to PC. So, the program counter will have the value M, and will start executing from instruction which is present in memory location M. But if the flag value is not 0, then from there itself you will come out and the PC will go as forward without having dumped the value of M into the PC. So, PC will be PC plus increment, and it will keep on doing it. So, here this will be very interesting to see how we will do it. So, again INS 3, so we are assuming that jump on 0 to M is instruction 3. So, only this line will be 1. So, only this finite state machine will be invoked. So, in fact, you can see that for each instruction there is a separate finite state machine which will be invoked. So, you can understand that different finite state machines will be there which will be hard coded. So, it will take some more area, but in fact, it will be extremely fast, because here you are mainly depending on the inputs which is nothing but your states. If you had lot of instructions, you could have optimized in this way that for many of the cases the initial states up to first 1, 2, 3 states are similar, then only it is deviating. So, I can make a more complicated type of a finite state machine. Say for instruction 1, 2 and 3, this is the finite state machine which is synthesized, because the first 3 are similar. Depending on the input, I can then bifurcate into some different branches, then again I can do it. So, of course, you will have an optimized hardware implementation, because maybe the first 3 stages are similar for everybody, last 2 states are similar for everybody. So, I could have made a merged machine and then keep on branching and joining, which will give me a better optimized machine, but it will be slower, because you will be now depending on the state as well as type of instructions, and again you will be joining and merging. So, this hardware size will be a bit small, but it will be a basically more slower design. So, if I have a full flexibility, then it will become a program, this is your microprogram based controller, which we will see later, but for the time being we are actually giving dedicated hardware for each instruction, and it is the fastest way of implementation. So, in this case INS 3 is enabled, that means your instruction at present is jump on 0 to this one, to some location. T1 will be similar. Stage 1 you are going to generate all the signals as output. T2 control step is 2, you have to wait till the memory is ready, so that you can get the updated value of program counter from Z out. Of course, you are storing the value of program count in the temporary variable y, because you have to add PC to your offset value. MDR, this is very similar. Instruction, you are dumping the instruction register from the memory data register. This is instruction fetch. Now important. Now we are saying that if T4, of course, if 0 flag is set. So now you see the inputs are 2. One is the state, other was your 0 flag. So this is an input which is coming from basically the external register, sorry, the register input, that is the flag register. This is an external input, that is from the memory. So this state depends on 2 inputs. This state depends on only one input, that is your state count. Here also it depends on 2 input, that is state as well as 0 flag. So if the 0 flag is set, then what you do, you take the offset, you add it to your y and basically dump the output to Z1. So Z in, that is actually now your Z is actually having the value of M, which is offset plus the program counter. All the details we have seen in the last unit. So now Z is actually having the updated value of, so if 0 is set, you update the value of PC with M, then you come over here and then what you do, you dump the value of Z to program count and N. So basically Z out, basically Z is having the value of M, you dump to PC, that is by PC in equal to 1. So now the PC will be having the M and you will start executing from M. But there is another choice, if the flag is not 0. So there is another instruction, another branch over here, same for the same state, if your counter has become 4 and if the 0 flag is not set, then what you do, you just generate the end signal and it will actually come to the final state and loop over. So the micro instructions will be stopped. So this shows a very nice example that if there is a conditional jump, then you can have a state where there will be a bifurcation. So here there are 2 types of inputs, state inputs as well as the inputs from the flags. And here there are again 2 inputs, one is the flag and one is an external input, which is basically your coming from your memory, that memory read has been done. So this shows an hardware control unit generation for a conditional jump. So from this discussion you can see that it is very simple to design the finite state machines which corresponds to different instructions. For each instruction basically you generate this sequence of inputs which will always be some states as well as the control signals which are to be output. And for some particular cases you have to also depend on some external inputs like from the memory. If there are conditional instruction you have to look at the flag registers, etc. And then just you have to go for a finite state based machine based synthesis which is a standard digital design fundamental, and you can make a hardware out of it which will be in terms of your flip flops and gates, and it will be done. But only thing is that it takes more area, because for each instruction you will have a different finite state machine. If I want to merge and make an optimization of it, it will be slightly having lesser area, but it will be slightly slower, and we do not try to do a trade off here. So what I try to do, whenever we have a hardware based control, we dedicatedly give for each instruction a finite state machine extremely fast, but you can just see that the area overhead is higher as well as a very non-flexible design. That is, for a given macro instruction, they are the micro instruction, and these finite state machines are basically hard coded. So again, if you just look at it, whatever I have explained, I have given you in the thesis, I mean given you this description in the slide, you can read through it, like that is the initial state S naught, the enabling condition is this, in T1 state these are the signals and so forth. At T2 you have to wait for WFMC and you have to go through, and most importantly you have to actually think about this state when we depend on the output of the flag registers. So that is what has been discussed over here, that if the 0 flag is set, which is one of the inputs, what happens, and if the 0 flag is not set, you directly go to end. So with this we come to the end of this unit, and just have a little look at some of the sample questions. Like for example, we say the first question is, draw the basic block diagram of a hardware control units of a CPU and explain its functionality. It's a theoretical question. If you are able to answer this question, you should be able to do it, because we have both discussed using examples as well as theory of how a hardware control unit works. If you are able to solve the question, you are basically meeting the objectives of associating control signals by looking at the control steps and basically the design issues and implementation of a control unit. So mainly this actually focuses on this one, and also slightly on this objective, because you have to also know what control signals are depending on what. But mainly if you are able to explain the whole control unit in terms of a block diagram, you are able to synthesize the idea of how to design a control unit. Then by different examples like load R1M, store R1M, add R1M, different type of macro instructions are there, then I ask you to design a hardware based controller out of it. So if you are able to solve this question, of course you are actually meeting both the objectives, because the second objective is the design objective, where you are asked to design a microcontroller, finite state machine based controller for a given set of macro instructions. And of course you have to also have a good analysis idea, because you have to associate different control signals with different micro instruction steps. So if you are able to solve this, your job is done. So with this we come to the end of this unit. From next unit onwards, basically we will try to have a look at slightly more integrated details, like what happens if you have multiple buses, how things are going to change, how many less number of steps are there, how the finite state machine synthesis will change. So we will be having a look at multiple bus architecture, maybe a 2 bus or a 3 bus architecture, and also we have to look in details about your, very importantly, your microprogram based control, because you have seen that in FSM based control it is very fast, but everything is hard coded and non-flexible. So we want to give more flexibility to it, because you can see that many of the instructions have several paths as common. So if we want to give some commonality and some flexibility, we will go for microprogram based design. And then also in the end we will see how all the things get changed if you have a multiple base architecture. We will just give an idea of it. So thank you.